So on Thursday, we left off, we were talking about an oil slick, and we spent quite a bit of time already on this, but just to kind of recap where we were, we had this graph that was representing the rate of oil flow in cubic meters per day. And so looking at this, I know this doesn't demonstrate a constant rate through the 2.5 or so days that it shows, because a constant rate, if you're looking at a rate graph, would be one y value, one dependent value throughout. And this isn't. It's got higher rate values at first, like maybe around 27 or 28 cubic meters per day, right near the beginning. And then we get lower as time goes on, and then it rises a little bit again, meaning, as we discussed, the oil's leaking quickly and then more slowly, but it's leaking the whole time. It's not going back into the oil rig. And then starts to leak a little bit faster again towards the end here. But what we have tools to deal with, and how we're going to make some approximations, and then we'll work on making those approximations better later, but just as a starting point, we're going to approximate by pretending that we actually have a constant rate for smaller intervals of time. So instead of looking at 2.5 days all at once, what I'm going to do is, and somebody asked what this number was from. It's just because I made an executive decision just as a making up a number. Suppose that instead of using different rates all the time like this shows, if I pretend that we have constant rates for 0.3 units, meaning 0.3 days at a time, along the independent axis. So we're going to pretend that, and if I were to draw something that has that, starting from the basics of this graph, I might think about, well, at the very beginning, it's around this 27, 28, so I'm just going to pretend that that initial value that I have a measurement for extends for the first few little units here, meaning like 0.3 is the number that I just declared. That's not anything that you'd get from looking at this graph, but just let's pretend, because 0.3 is relatively small, but on this graph it's big enough so that we can see it. It's not microscopic the way it's zoomed. So if I just pretend that I have that 28-ish value for a little bit, this is what an exact constant rate of change function, this blue line, would look like if it extended from time 0 through time 0.3 at one constant rate. And just by choice, using the constant rate that this graph looked like it had. So if I wanted to continue this process and say, well, yeah, so clearly this is good near to 0, and the farther I get from 0, it's a poor approximation, worse and worse as I go in this case. So eventually, no matter how wide my interval is, I'm going to want to re-estimate. So instead of continuing to use 28 all the way across and having one constant rate, I'm just going to use for 0.3 days at a time. So at time 0.3 days, however many hours that might be, into this oil spill, I'm going to pick a new rate and use that for the next 0.3 days, and so on and so on. And I could do this indefinitely, but notice, for instance, at time 1.2 through 1.5 days, that's a pretty good estimate. So the size of the interval doesn't determine what makes it a good estimate or a bad estimate. That's dependent on the exact shape of your graph, how close it is to being a constant rate of change. And right around 1.2 to 1.5, it's not a constant. It's still curved, this rate function, meaning it's changing the dependent value throughout that interval, but all the dependent values are fairly close to wherever this small y value is. Maybe it's about 3 cubic meters per day. So in any case, if I wanted to use this technique, the reason I'd want to use it is to be able to utilize my constant rate of change relationships, dy equals mdx, if you have a constant rate m that relates your variation in independent variable to the resultant change in your dependent variable. So if I just pick one number at a time to use for a little while, I can see what happens during that interval, or how what happened during that interval contributes to an overall amount of, in this case, oil that's spilled by later. So on the worksheet that you have that I handed out, or it's available on Canvas if you weren't here on Thursday, Um, this is called R. So R sub V was the exact rate of change that what's up on mine, the curve here, or it's red on here. So R sub V is the exact rate of change of the volume of the oil as it's spilled, measured in cubic meters per day. And this R, this blue function, is not a great approximation, but it's an approximation to this. So we're just going to call this R without a subscript, as like a fake rate function. It's an actual rate function. It's just not exactly the same as the one that I'm estimating from. And it's not even particularly close in some places. But as a starting point, let's pretend I had 5 different constant rates of change, each one extending for 0.3 days. What I'd like to know is how much oil has spilled based on that estimate. So before we do any formal writing out of functions as at the bottom of this, let me get this going. That's the scary looking stuff, but don't worry about it. So let's see if this will go or if it'll close on me as usual. There we go. So for instance, if I wanted to know how much oil spilled in the first 0.3 days, if that's all I wanted to know, in the first 0.3 days, meaning between time 0 and time 0.3. If I look at this graph, I'm like, well, between 0 and 0.3, if I use this blue rate function as my estimate, as my rate, say, okay, just thinking numerically, not writing this out with symbols and function notation just right now, but if I look at this like, oh, maybe that's about a rate of 28 or so. It's above the 27.5, just a little bit. So maybe this is a rate of about 28 cubic meters per day for the first 0.3 days. So if that's the rate, how would I compute how much oil spilled during the first 0.3 days? Yeah, 28 times 0.3, right? If I want to know how much spilled, that's during this interval, then that's a change in my Y, eventually, my amount of oil spilled, mdx. I just want to know I have a rate, I have an amount of time that passes in this case, an amount of change in my independent variable. So how much is accomplished because of that rate while I'm using this rate m, which is about, based on the picture, 28. During that whole interval, it would be 28 times 0.3. And we could multiply that out. Was it 8 point something? 8.4, right? Now 8.4, what's would this be? Units. 8.4 cubic meters, right? 8.4 cubic meters. I'm going to write CUM. So it doesn't look like our rate is being cubed, m cubed. So during this interval, based on our estimate, we'd have 8.4 cubic meters of oil spilled. Now, what if I'd asked instead how much total oil was spilled? I'm just going to write how much was spilled between time 0 and time 0.7. So 0 through 0.7. Well, that 8.4 is part of it, right? Because that spilled during the first 0.3 units. If I'm going to use this blue fake R function here, it's really a rate, but it's not the actual rate, it's just an estimate. If I want to use that and go up through time 0.7, how many different rates does our estimate rate function, does function blue R, have during the interval time 0 through 0.7? You got 3 different values, right? The whole 8.4, so that 0.3 days at about 28 cubic meters per day, just visually estimating. And then a different rate, let's just say this one's about 20. It's pretty even with that. So if I say that this rate here is about 20 cubic meters per day, seems reasonable. That goes up through 0.6 then. And then I'd need to use this third rate for a little bit too. This one would apply from 0.6 to 0.7. So let's see, what's that one look like? About 12 and a half? I'll just say 12 to make it easier to work with. So if I want to know how much oil was spilled in this first 0.7 of a day, first 7/10 of a day, if I want to use this constant rate of change method, using this setup here, I'd use 3 different rates. So this is similar to some of the stuff you did on homework. I hope this sounds familiar, that was only for full intervals at a time. But I'll use that largest first rate for the first 0.3 days, and the next 0.3 days, I use a different rate that's slightly smaller because of the way that this graph goes. And then for the last, well, not 0.3 days, I only want to go up to 0.7. I'm going to use this smallest rate, which is about 12 cubic meters per day. But if you see, it's kind of a repetitive process. If we do this one interval after the next, I've got my first rate times 0.3, and my second rate times 0.3. And it's just that for my third rate, if I want to do this numerical computation, I don't use the third rate for a full unit because this doesn't extend to the end of that interval, doesn't extend all the way to 0.9 where this would end. I've only got 1/10 of a day left. So this computation here with whatever numbers you estimate for those, 28, 20, and 12, this part we already did. This is 8.4 cubic meters of oil spilled, and then in the next one, this would be, let's see, this was using 20 times 0.3, another 6 cubic meters of oil spilled, and then in this last, well, not the whole time that we were using that rate of about 12, but for the next 10th of a day, 12 times 0.1 would be about 1.2. And then I could add all those together. This is the accumulation during the first interval, the accumulation or the amount of spilled oil that builds up during the second interval, 0.3 to 0.6. And here's what remains in that end interval that we're kind of in the middle of right now. If I say up through time 0.7 days, this 1.2 cubic meters here. And so we get to add these together. Now what I'm going to call these is what you see kind of down at the bottom. This is an approximate amount of total accumulation up through time 0.7. So just estimating numerically, I could say that I'm going to use capital A for accumulation. And you see A of t down at the bottom of this sheet as a function. We'll write out some function rules in just a moment. But what I mean by accumulation, again, is how much happens, just kind of in a general sense, due to using a rate. And we're measuring this by adding up as if we have constant rates over, not just one constant rate over the whole interval, but several constant rate. We're going to use a constant rate over several different small intervals. So A of 0.7 would be the accumulation up through times 0.7. So to emphasize that it's starting from 0, not just in this case where the oil spill just started, so obviously we're starting from 0. I'm going to refer to this as net accumulation. This big capital A stands for net accumulation, just meaning just talk about what you can determine from the rate itself. Don't worry about what might have happened before in terms of your computations. Don't worry about a starting value other than 0. Just wherever in time, or whatever your independent variable is, whenever we're starting, start from a dependent value of 0 for the accumulation and just build upward from that. So just use the rate to generate amount of stuff. In this case, just use time and our rate to figure out how much oil there is. Maybe the oil was spilling beforehand, but we just didn't have a function to model its rate earlier. But during these 0.7 seconds, so the accumulation or the net accumulation during the, not 0.7 seconds, 0.7 days, during those 0.7 days, the total amount accumulated based on our estimate is about, what, 15.6, 8.4, 6, and 1.2. And that's cubic meters of oil spilled. So this is just doing a numerical problem, pretending, like we know what those values are. Now, as we've done either in GC or in homework questions, instead of just making up numbers saying, I think this is about 28, if I wanted to express this y value here, whatever it is that looks to be about 28, by using some function notation, that is, if I want to define function r, here, I can use function notation to do that. Now this looks all messy and slightly frightening, but this is just a piecewise function. It's piecewise constant. If you read the top row, first look at the domain. It says t is between 0 and 0.3. So starting at time 0 through time 0.3, there's one symbol that doesn't have any variables in it, just a function name where that function is evaluated at 0. So thinking about what this means, this is referring to the value at that spot right there, which we said is it looks like about 28. R sub v of 0 is referring to the dependent value on the red curvy graph when the independent value is 0. So this is the value of the exact rate function when time is 0. So it looks like about 28, but to express it precisely, I could just say r sub v of 0, and that refers to whatever that height is exactly. If we had a function rule, we could compute it, but as we don't, we can express it exactly using function notation. So it's just saying I'm going to use the y value, the dependent value of this red curve, not only at 0, but I'm going to use it for the full interval 0 to 0.3. I'm going to call that a part of this approximate rate function, regular r, without the subscript. And then the next interval, when t is between 0.3 and 0.6, I'm going to use a new value. What's the value? Well, it looks like about 20, but to express it precisely, it's the dependent value of the red curve that corresponds to a time 0.3. So it looks like 20, but I can call it r sub v of 0.3, and I'm not just going to use that single point. I'm going to use it for a full 0.3 of a day. So I'm using one value of the red curve's function, so picking 5 different values in this case that cover up through 1.5 days into the oil spill. I could have continued going, but just ran out of space on here, so we could continue this indefinitely and use these constant rates. That way I can generate an amount of accumulation within each interval. Now, as we said, it's not a particularly great estimate, but I think we talked about it on Thursday. If I wanted to get a better estimate, I'd maybe just make my intervals smaller. And I think you examined this as a part of your homework, where you compared one big chunk of estimating constant rate for 1 full second versus 0.2 seconds at a time, 5 different times. So this is just using 5 different values of the red exact rate of change function. But instead of just using them for a small moment, we're using them for 0.3 days at a time because we can see this and we can do some computations in a reasonable amount of time by hand. Now, if I wanted to make this better, I'd set computers to work doing this. But as you notice, it is kind of repetitive, this process. So, take the rate, multiply it by how long you're using it. Take the rate, multiply it by how long you're using it. If you want to find an amount, like a value of accumulation. Now, what we're building to between today and Thursday is figuring out how would I just express in general a function that determines my amount of accumulation based on my independent variable. So if I say, a of 7, I can just plug in a 7 someplace and get an answer for that. What would I have to plug into? Not, well, I'd need to pick 3 intervals and then I'm going to do all these separate computations. How would I write down the function that does all those computations for me? That's what we're going to try to worry about. And we can also think about not just doing numerical computation for it, but looking at the structure of that function on its own so that I can imagine as x increases, or whatever I call the independent variable, x, t, whatever, as that increases, what happens to my amount of accumulation. So as a start, just using our numerical computations we did a little bit ago, thinking about, let's say I want to graph an approximate accumulation function over here. So net accumulation, we're going to start at time 0, and net accumulation functions start from 0, meaning just increase or decrease due to the rate. This time we're increasing because we've got all positive rate values. But just as a start, the first thing we did was, well, how much accumulation would I have by time 0.3? How much oil would have spilled by time 0.3? We said that was just 0.3 times, this looks like 28. Now, in order to be able to do a graph, I'm going to use some approximate numbers. So if I say that this rate is about 28, like we did before, I know that by the time I get to 0.3, which is that spot, I should be at 0.3 times 28, which is about 8.4. So just as a rough estimate, big dots always makes your estimates look better. By time 0.3, I would be at that spot. Now, what if I was anywhere between 0 and time 0.3? How do I need to calculate those all separately to know where the graph is going, or do I know what shape this approximate accumulation is going to be between time 0 and time 0.3? Is it curved or is it straight? Well, if there's an exact accumulation, I know the rate's changing all the time. It goes from 28 down to something else. But if I'm using this approximate rate, I'm going to use a rate of 28 cubic meters per day the whole time from 0 to 0.3. If I have a constant rate between 0 and 0.3, and I'm graphing not the rate but the accumulation, I should have a straight line, not horizontal, but diagonal, connect the dots, right? So it'd go like this. Now, if I wanted to express that set of points, all those points that lie between 0, 0 and 0.3, comma, well, whatever it is, it's about 8.4, but we can talk about function notation usage in a bit. All I need to do is say, oh, well, I need the rate, and, well, I know this one starts at 0, so this one's an easier one than some of the others might be, but like y equals 28x, something like that. Use the letters of the problem. Maybe it's a of t equals 28t for t between 0 and 0.3. So that would be an approximate. I could say a of t is approximately 28t if t is between 0 and 0.3, right? Now, a is an approximate function. This is an approximation of approximate. This 28 I just made up, right, just from estimating from a graph. If I wanted to say more precisely what this is, instead of writing the number 28, I can just use the symbol r of t. I could say r sub v of 0 also, because that's the rate that we're using. But r of t between 0 and 0.3 is r sub v of 0. So I could also say this approximate accumulation during this first interval here is just r of t, my approximate rate function, times t. Right? Because I'm starting from 0 and building up from there. Now, I'm going to erase some of this, because after that, if I wanted to know what happens afterward, I'm going to write this in an easier spot. So this section, the rule for it, the function rule, half of it would be about, well, it'd be about 28t, or r of t times t. Not times 0.3, that would just give me this spot at the end of the graph. This is a formula for that line segment between 0 and 0.3. after that, I'm going to change rates. And if you want to, you can imagine, okay, it's about 20 for the next 0.3 units. Or between 0.3 and 0.6, the amount of oil spilled is still going to increase, but it's increasing slightly more slowly. Over that interval, I should see, let's see, so if this is about where 8.4 is, over the next interval, I should see it increase by, let's see, about 20 times 0.3, so about 6. So going up about 6 units from there, which is 14.4. Or, let me write in red here. The amount of increase is 6 due to the second interval. During the first interval, my amount of increase equals the ending y value, 8.4, because I started from 0 and went up 8.4, went up mdx. dy equals mdx. During the next interval, I also went up mdx, but with a different m. Now, that just helps me figure out where the end point is. If by 0.3, or 0.6 rather, 0.3 units later, I'm at this spot 14.4, this is another line segment, although it's kind of hard to tell in my slightly messy picture anyway. It's a slightly lower slope, slightly less rate of leakage of this oil. But if I wanted to write the equation for this line segment, I don't start from 0, I start from 8.4, right? I start from the mdx I had from the full interval last time. And then I increase at this, well, it's still going to be r of t, but it's about, numerically speaking, 20. Now, if I want to write an equation for something, I'm not starting at the origin like last time. It's not quite as easy. I need mdx as this amount of change, starting from 8.4 and increasing at a rate of 20 cubic units per day for each unit I go past where I started from. So here's my starting point. I want to measure dx relative to that point. Just like I'm measuring my dy as adding on to this starting value, y initial plus dy. Well, I find dx by comparing to time 0.3. So if I'm at the end, if I'm at 0.6, I know that that would be 0.3 later. But anywhere else in between, like if I'm at 0.5, if I'm at 0.5 days into this, in the second unit, in the second interval that we're using, I'm only 0.2 into that. I need to compare whatever my t value is, whatever my time value is, to the start of the interval to find dx. So if I need to know how long that is, I need to be thinking, oh, well, how far am I from 0.3, the start of the interval? So t minus 0.3. Now this is the numerical version of it. That 8.4 was really my first rate times t, and then by the time I'm at the end of that first interval, it was my first rate times 0.3. During the second interval, I've got y values, meaning total accumulated oil, 8.4 plus whatever happens during the second interval. By the time I'm at the end of the second interval, I've got 8.4 plus 6. But the way it is here with this t in this is to represent all the points within that interval. Because if I want to represent not just how much oil is spilled by the end of each interval and have just a bunch of different total numbers, if I want to have a formula that would tell me the amount spilled at any point in time, like we did when I said find the amount of oil spilled after 0.7 days. Well, figure out all the full intervals and then add on the little extra from whatever interval you're in. How far are you into that interval? Use your rate for that amount of time. So I'm going to put up something kind of line by line here that looks a little bit overwhelming at first, kind of like the rate function did. If I can get this to go. There we go. But this accumulation function, because it's much neater writing on the computer than my writing it, but this is just mdx. So if we're starting from time 0, now I didn't write minus 0, but you'll see it kind of matches a nice pattern with the others. What we're looking for is to make a nice pattern out of this so we can write it more succinctly. But in the first interval, I'm starting from 0. And so all I've got is an m dx sort of expression. If my time is between 0 and 0.3 days into the oil spill, I'm going to use the rate given by fake function that only has 5 constant rates here. So one of those numbers times how far I am from 0. Because I'm going to be using just that first number as the rate. It's r sub v of 0. But I'm going to use that first number times, well, this could be anywhere from 0 to 0.3. Right? Depending on what value of t you plug in, you're going to use that first rate for some amount of time. If your t value is something past 0.3 but less than 0.6, well, you'd use that whole like 8.4 number, r of 0, or about 28 times 0.3, plus what happens after that. So in terms of how this is the more symbolic version of what I had up before. So again, this is just m dx. If I'm in the first interval, dx, generic letters wise, dt in reality, is how far I am from the beginning, which in our case was 0. How far is t from 0? And I use this rate m, which is defined over here. If I'm in the second interval here, if I'm between 0.3 and 0.6, I have some oil that already spilled, like that's at 8.4. And then, depending on how far I am past 0.3, I use that distance, that dx, times our second rate, times the approximately 20 number. It's still r of t. We find it over here. In exact form, we're using this rate, r sub v of 0.3. But if I'm anywhere within this interval, I'm going to have 8.4 for sure, plus some extra, plus whatever accumulated during the second interval that we're in the middle of. So take a minute, see if you can figure out what I would need to write the third piece of this piecewise function. If I've finished the whole first 2 intervals, I'm somewhere past 0.6 days into this oil spill, but not to 0.9 days yet. See if you can kind of extend this. Think about how much do we have to already have at rates that we're done with, plus, depending on where we are within the current 0.6 to 0.9 interval, how much more will we have due to that third new and improved rate? Very good at drawing straight lines. They all look curved. so again, that R of t times t minus 0 and R of t times t minus 0.3, both of those represent that constant rate of change, MDX sort of piece, as t is increasing from 0.3 to 0.6, using that new rate, the current rate, the red R rate, whichever one actually applies during the interval we're in. This part's still growing, but we're already past a certain amount of this. So we know what's in our past, or we know how much oil is already spilled at earlier rates. Now that we're using this, in this case, third rate, which looks to be about 12 or so, now that we're using this third rate, we're going to be accumulating oil or adding on additional spilled oil to our past amount at a slower rate, but it's being added on. And we could figure out where, like, this point at the end, at time 0.9 would be, like what we're building up to, but we need to be able to write the equation of the stuff in between too, which means I need my starting point and then a rate of change afterward, y initial plus MDX. And there's a lot of different ways you could write this, combinations of estimating numerical values off the graph or different function notations. In fact, one thing I want to point out right here, notice this says R of 0. R of 0, if t is 0, that means I'm using this. R of 0 is the same as R sub v of 0. So if you wanted to write R sub v of 0 instead of R of 0, that's actually the same. R sub v of t and R of t aren't necessarily the same, but they're both the same at 0, at 0.3, at 0.6, at 0.9, at all those places where we stop and change to a new rate, because that's how we defined it. But moving on to this next line then, to talk about what's happening during our third interval, we have to have a starting point of what do we have done already from the first two intervals, and then add on due to the current interval. So what I have in blue here refers to the stuff that already happened. What happened in the first interval, R of 0 times 0.3, whether that's about 8.4 or whatever, plus what happened in the second interval. I used that next rate for another 0.3 days. So this is all completed accumulation, intervals that we're done with, whose rate values we're not using anymore. Plus, well, if t is between 0.6 and 0.9, depending on exactly how far between, I'm going to use that next rate, the rate that applies to t between time 0.6 and 0.9, for a little bit. Anywhere between 0 and 0.3 is how far I'm going to use this, because those are the sorts of results I could get here. How far is t past 0.6, past the beginning of this interval, or how far is t into this current third interval? So we could do this again, and it gets longer and longer and more tedious, but if you can see kind of the structure of what's going on, and in symbols, it's slightly less annoying, even though it's longer to write, than trying to work out all the numbers. But the stuff that's in blue here is representative of our y initial. So it's a combination of all the stuff that we accumulated in the first 0.3, the second 0.3, the third 0.3, however many full intervals we've gone past in order to be talking about the piece of the piecewise function in question. So if we're between 1.2 and 1.5, so if we're in this section down here someplace trying to estimate accumulation, I know I've already got 4 full 0.3 days intervals worth of accumulation that I'm already done with, nothing's changing, that's over. But I'm adding on at this new fifth rate, the rate that applies between time 1.2 and 1.5, R sub v of 1.2, or about, I don't know, 3. Using that for the last, well, however far I am past 1.5. Although this, or 1.2, sorry, typo. Let me fix this, because that's not good. Yep, sorry. No. But this number here, if I can get my pen to go back on, This is supposed to be a 1.2. However far I am past 1.2, as long as it's not past 1.5, that's our dx, or how far we've gone into this current interval. How long have I used this most recent rate for? And so if I were to look at a graph of this in general, now I was trying to draw this and I just gave up. Not so good at drawing straight lines with this thing. But if you can imagine, over the first interval I've got a line with a high slope, fairly steep, or visually speaking, going up faster than any other part of this accumulation graph. It goes up vertically, indicating more oil is spilled the whole time, but at slower and slower rates. Straight line that's less steep, straight line that's less steep, and so on and so on. This one's the least steep. So overall, let me go back to what we talked about the very first slide of this back a while ago. If we're trying to imagine a function v that gives a total amount of oil expelled, not our approximate accumulation, which would be piecewise linear, lots of linear segments, you can see, oh, it goes up from 0, steepest at first, and then less steep and less steep and less steep. And we only went up through 0.5. That's where we stopped our estimations just a minute ago. But this visual, we can get things that are fairly close to that using our techniques of constant rate of change, despite the fact that in that last graph that we did, when we estimated that rate function, we know that was a poor estimate. It wasn't particularly close. Maybe if we did 0.1 day at a time, we could get something that's a lot more pieces in that piecewise function and kind of ugly, but it'd probably be closer to looking like this. It'd be less easy to distinguish little chunks of straight line from a curve, and they'd probably be closer to being at the right angle, so to say, the right slope or the right steepness. So this is our goal, is to make functions, and what we were just doing, we were writing a function that models what happens because of the exact rate function r. That's hard to use, but if I make a poor approximation of it even, I can come up with a way to describe that approximation in general, and then a way to describe the associated approximate accumulation, net accumulation starting from amount 0 in general, where writing out all the details is a little bit tedious, but if you can see it's repetitive, you can kind of see there's a pattern. That's good. That means there should be a shorter way to write it using math notation. So what I'd like to do to start with, let's see, I'll pass this out first. Two-sided sheet of paper here. It says task 1 on one side and task 2 on the other. We're going to look at a very similar example to this where it's in section 5.1. But actually, so that's what I asked you to have seen this. But it's similar to what we just talked about. The first task is to estimate the height of the rocket due to knowing the speed at which it's rising at an upward velocity just said, well, let's just say we break this up into 0.3 days at a time. So I want to call that a specific item. Let's see. There we go. So here's our situation in motion. So what I want to do in order for us to be able to talk about how we're doing our estimates is by me giving you that 0.3 days in the oil spill. That's setting a number that we're just going to use. It wasn't, we could have made something smaller. I just chose 0.3 because it was useful and we can picture it. But that was a parameter in that problem, in that we could have chosen a different number and used it throughout, getting slightly different results, but it'd be the same general process. So what we're looking at here is a rocket-powered basketball that's rising at varying heights, and we actually have a formula for, there we go. We have a formula listed on your sheet that you've just gotten that says what the equation, what the relationship is between time elapsed and this vertical velocity. So this function v, first of all, so we've dealt with both sorts. Is it a rate of change function or an accumulation function? It's standing for the velocity at which this rises. That's a rate of change function. It's describing the rate at which the height changes. Now I could talk about its rate of change also, but this is measuring the rate at which the rocket ball is rising. So it's a rate of change function. If my goal is to tell how high this ball, this rocket-powered ball is at any point in time, I'd need to have some particular values of this velocity if I wanted to do some numerical computations. If I want to be able to express the height at any point in time, then I need to take my velocity expression, whether just calling it v of t or whatever, and use notation to express how its height is related to that velocity at any point, depending on what point in time we're using. So we want to develop, as I said, this net accumulation function associated with v. Just quickly, I've kind of already said this, but in the accumulation function associated with this velocity, where we've got the velocity measured in meters per second and time elapsed since launch measured in seconds, that's our t. If I'm looking at what happens because of that rate, assuming I don't do any weird unit conversions, what would be the units on the accumulation due to this rate? What would be the units on how much height it has? Meters per second? Meters? Seconds? Meters, right? Meters is a measure of height. So unless I do some weird computations and get the height in kilometers or feet or something else, if I just work from this rate and use time, the independent variable, in seconds still, I'll end up with height measured in meters. dy equals mdx. Changes in the height over time depend on my rate in meters per second multiplied by a given number of seconds. But as a starting point, if I want to know the coordinates on this graph, let's see if I can get it to pause sometime. There we go. At time 5, if I want to express the coordinate point on this v graph at time 5, I can call it 5 comma v of 5, right? I could say, oh, it looks like it's about 9. Or on your sheet, you can see the formula for this also. But let's see, what is it? It's like the 1.3, t to the 1.3 power. But what's more important of this is you remember what the meanings of all these function notation symbols are. So v of 5, v, if this is the exact rate of change of this rocket, height with respect to time, so the exact velocity of the rocket in meters per second at any moment in time. If I want to know what v of 5 means, it means this here. the rate of change of the height at the moment when t is 5. So imagine we have to wiggle a little bit away from t equals 5 to have some change in, some increase in time in order for the height to be increasing, as we can see that it is. So if you freeze time and look at 1 instant, you don't have any change. If you wiggle forward a little bit or look at a small moment using a constant rate v of 5, we can see what the ratio is between the height change and the amount of time elapsed, or the time change. So, keeping in mind, dy equals mdx, v of 5 looks like, 9 point something, but at the moment t equals 5, any incremental adjustment to time, any additional time that goes by, the extra height that's added on, I know it's added so I can see this is positive rates, is going to be v of 5 times as much. So the increase in the height of the rocket, measured in meters, is going to be v of 5 times whatever my incremental addition of a little bit of extra time is. So if I allow a little bit of time to go by past time 5, I can use this rate v of 5, multiply by it to figure out the little dy, the change in height of the rocket during that small interval. All right, so let's get down to some computations here. So assume the ball starts on the ground. Or assume we don't care where it starts, and we're just going to talk about how much height it gains after that, but let's say it starts on the ground. I'm going to use a value of 0.9. I'm going to call this delta t. dt, I want that to be any width that I want. I want that to be able to vary within any of my little intervals, but I'm going to use delta t just for sake of calling it something. I'm going to break this up into intervals of width 0.9. So I'm going to say that my delta t, my incremental sizes of time that I'm looking at one at a time, and using one rate within each of those intervals, those are going to be 0.9 seconds wide, just to have something arbitrary that isn't 1. The reason I'm not using 1, although it's easier to compute with, is because it disappears a lot. It's hard to see what's going on if you just use numbers like 1. So I'm going to use 0.9 seconds at a time. Every 0.9 seconds, I'm going to reevaluate my rate and use a different value of it in order to generate an approximate accumulation function from this. So this delta t, by my saying delta t is 0.9, is that a variable or parameter? That's parameter. And again, this is kind of like rules for the game. Let's pretend delta t is 9, or let's pretend we're using widths of delta t and let delta t equal 9. I could change that, or let's say I were writing a program in GC to compute these long things for me, and I define delta t to be 0.9. I could go back and change it to be 0.1 and not have to type anything else other than that. If I can write it, bang, suddenly all new calculations with a much better estimate. So let's just call it delta t, and I'll say that that's 0.9. So I'm using this delta symbol to indicate the width of the intervals that I'm using. dt, on the other hand, is always expressing how far I am at any point into the interval, or how far I've varied into the interval that we're in at the time. So I'm going to pause this graph in a moment, but you have it kind of frozen on your sheet already. On the task 1 side, you can see this with, let's see, just do it this way. You can see this graph. What I need to do if I want to use this exact rate of change function to figure out something, I need to have constant rates of change. That is, I can't have this changes all the time sort of situation. I need to be able to describe my interval widths, and using each rate one at a time over a small delta t, 0.9 seconds interval, and talk about which interval I'm in and how many rates I've already used and be done with from earlier intervals. So if I want to sketch an approximate rate of change function, that's our first step, talking about how do I make this exact rate of change function usable? How do I make it fit my rules of constant rate of change, dy equals mdx? And so we just pick a few points and use them each. Pick the y values from those points and use them for a little while at a time. So, meaning, like you see on your graph, I'm going to use one rate at a time for a while. Each one of these is being used for 0.9 horizontal units, 0.9 seconds, before I jump to another one. And again, just like before, we're starting from the beginning, so use the value that we started with at, in this case, time 0, but whenever. Use the rate from that beginning of the first interval for the full first interval. Use the rate from the exact rate of change graph that applies at the beginning of this second interval. Use that for the whole second interval. And so these horizontal line segments are this fake rate function or our estimate rate function, an approximate rate function that we're going to be actually utilizing. So if I wanted to find the height of the rocket by time 5, and I've got intervals that are 0.9 units wide, so this is time 5 seconds, and I've got 0.9 units, 0.9 seconds per interval. We had a slightly easier problem with our oil spill, it's just in the second interval or third interval or something. But if I want to find the approximate height of the rocket, you could write this out with any combination of estimating numbers as you see them on the graph, using function notation, or since we have a function rule here, v of t equals t to the 1.3 power, you could even write out using t to the 1.3 power as that function rule. But think about how you would compute the approximate height of the rocket using our approximate rate function here. So think about how many full intervals we'd have, how many intervals we've passed, how far we are into the one we're in the middle of, and so forth. So you can estimate, it says symbolic and numeric. See if you can come up with any way to write it. We'll talk about a couple of different ways, but there's several, or combinations thereof. How to express or how to compute how high is the rocket by time 5, assuming it started on the ground. by time 5 seconds, how many full intervals have we passed if they're 0.9 seconds apiece? How many complete intervals? 5 complete intervals. So we're in the midst of the 6th interval someplace. How far into the 6th interval do we have to go to get to time 5 seconds? Yeah, so we're looking for how far are we from the beginning to 0.5. So if you think about these are 0.9 at a time. So the first interval is 0 to 0.9, 0.9 to 1.8, 1.8 to 2.7 to 3.6 to 4.5. The next one would be 5.4. But between 4.5 and 5, this is the stray computation that's different from the rest of them. If we're computing how much, we've got a different rate for each interval. But for each of those full intervals, the ones that we've gone through the whole thing already, we do, that MDX sort of expression. We're going to use the whole delta t, the whole 0.9 for it. So those completed intervals, as compared to the current interval, the one that we're in the middle of when I'm talking about time 5, they're the same general structure. It's an MDX, or rate, times the amount of, in this case, time for which I use that rate. It's just that for the first 5 rates, I use them all for 0.9 seconds. For the last rate, we get to use it for less than that. So a couple examples of ways you could write this without estimating off the graph what the actual rate values are. I could talk about, well, other than the first one, 0. If t is 0, that rate that I use for the first part, this doesn't start up at 28 like our previous rate graph did. It starts at the origin. And you can see from the function here, it's not just close. If t is 0, this is 0. So our rate of 0 for the first 0.9 seconds, a rate of, well, 0.9 to the 1.3 power for the next 9/10 of a second. 1.8 is the t value that we use for that third interval, and then 2.7, 3.6, and so forth. But we've got 5 complete intervals, and we could express this. I use the V notation. Your worksheet and my slide also say R sub h, if you want to use the notation that's more standardized, a rate of change of function h for height. So this is just a couple examples, but all of those are times delta t or times 0.9 because, well, we've completed those intervals. This t value of 0.5 is past all of those. We're done using those 5 rates. But for our current interval, we've just got one small computation. Maybe I'll call this dt, how far I've moved past the beginning of the interval, which isn't 0.9 yet, it's only 0.5. So I could also just call it 0.5. I could call it t minus 4.5. There's a lot of different ways to express these things, and like I said, this is just a couple of different ways to combine symbols and numbers and formulas in order to piece together this computation or an expression for this. But what I wanted you to notice about this is, again, the repetitiveness of it. It's like, oh, well, all the completed intervals I do MDX, 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 and I change the m every time. I change the rate that I'm using every time based on looking at the rate at the left side of the interval for the exact rate function. And then I multiply it by the width of my intervals. The only one that's slightly different is this, and I find the rate the same way. The rate at the left end of the interval, all that's different is, well, it's not delta t, it's not my parameter width. The width that I use it for depends on how far I am into the interval. So if I were talking about not just doing a specific computation, finding the height by time 5 seconds, if I wanted to express the height for, well, after t seconds, I'd need to know what interval t is in. Is it in the 17th interval? Whatever this is, based on how large delta t is, and how far into that interval is it. And then I'd figure out, oh, all the completed intervals, I'll just add those all. It's pretty much the same expression over and over and over again, but it'd be with numbers. The variable would show up only in that last part, which interval I'm in, although the variable also determines how many full intervals do I have. So in any case, what I want us to do, and this is what we're going to finish up on Thursday, is work from this and recognizing the repetitiveness of this process. We're going to work to combine this with sum notation, big capital sigma, used for adding up things. When there's a formula for what it is you need to add up, if you notice these expressions like number one, oh, it's a rate times a delta t, a rate times a delta t, a rate times a delta t. I just need to add up a bunch of those, and they're all the same structure. We can do that using capital sigma. In your reading, I'm going to have you read something about summation notation. If you're not familiar with it, take a look at that. But we will finish up details of how to do this in general for a generic, any sort of rate function, any sort of interval width. How do I piece this together? We'll put this all together. I'm also going to post a video for you to look at that shows kind of a general process and some things pointed out on graphs, a GC file, that we're going to take a look at that at the start of class on Thursday, about this whole process of starting from an exact rate of change function and making an approximate change function, and talking about some of the things we need to pay attention to and compute as we're trying to generate accumulation. All right, that's it for today, though. Thank you.